Alright, so this video I'm going to go through some ways to search through an array or an array list. So the first thing we're going to talk about is something called linear search. And the idea is that you start at the beginning and you check each spot until you find what you're looking for. So let me go ahead and open up this little search widget here. And the idea is that this is an array that has 31 spots in it. Zoom out a little bit. And we're just going to try to find the value 819. So we just kind of search around, and you can see the values aren't in order. So there's no way to find the value by any other technique by just checking. You can see that I found it roughly in the middle of the array. And that's what you should sort of expect on average. Sometimes you'll find it at the very beginning, sometimes you may find it at the end, sometimes you might not find it at all. But if you do find it, on average, you'll find it roughly in the middle. Alright, so with that in mind, let's look at the code for this idea of linear search or sequential search, what that would look like. So this shows you a method called locateValue, and what it has is a parameter, which is an array of numbers and something that we're looking for, and we've got a loop that's going through every position in this array one at a time. If at position I in the array we find the target value, well, we're going to report that position as our location. And so we also need a way to locate or indicate that we haven't found it. And so a common indicator for that's -1, because -1 is not a valid position in the array. So just to check to make sure this makes sense, we're going to look at, oh, I clicked the wrong button there. We're going to look at this code and what happens if we try to call it. So I'm going to call this locateValue method with a given array. 314159 are the values in it. And we want to know what happens if you call this method and the parameter, the second parameter, the target value is 4. And so based on what we just described, what it's going to do is find the location where the 4 is in the array. And since that location is at position 2, this code is going to return the value 2. Now let's look at another one. What happens this time if instead of searching for the value 4, we're searching for the value 2? Well, because 2 is not in this array, this loop will never find it. So what it's going to return instead is the value -1. Here what you can see is I changed the method to work on an array list instead, so it's an array list of integers. The only thing that has to change in the code is instead of nums.length, it's now nums.size. Instead of nums bracket I, it's nums get I. So everything else is the same, but the two list commands here have replaced the array commands. Now, what if we were looking for not where a value was, but just whether it's in an array or a list? Well, if that's the case, let's say we have an array list of strings, and we're looking for a given target string value. Well, you could use a for each loop instead of the indexed for loop. So I could run my for loop starting at the beginning. I'm going to take out each value one at a time and from the words list. And if that value dot equals the target, so I'm using dot equals because that's the correct way to make sure that two string values are equal. You don't have to do dot equals for ints, but for strings you do. And you would do something similar for really any type of object. You want to make sure that you're not just using equals equals for objects. So if I find a match, I'm going to return true, and if I don't, I return false. So the last thing we're going to do with linear search is look at an example involving complex objects. So I've got a student class on the left, and what a student has are two properties, a string name and an int ID. I have a way to create a student, and I have a couple methods that I can call on student objects. Now I've got another class on the right called Literacy Center, and it has an instance variable which is an array list of student objects named students, and we're going to assume that this has been created for us. And so what we're going to do now is finish this method called add yourself, and the goal is to add yourself to this array list of students. So before you can add yourself to the array list of students, you need to realize that what we add to it has to be a student object. So we need to create a student object, which I'm going to call me. And when I construct a student, I need to put in two parameters. One is my name, so Mr. F, and then an ID, which for this example I'll just say is 5 ones. So that creates a student object, but it does not add it to the list. Because the name of the list is students, I write students.addMe. The directions don't say where to add it, so I'm just going to add it to the end. A variation on this, which is a little bit shorter, is I could take this command and just put it where me was. So this says students.add new student Mr. F 1111. That creates a student object and adds that creation to the list without storing it in a variable to begin with. Now, this one's a little bit trickier. What we want to do in this problem is determine which student in this list has the given ID number. And we specifically want to know their name. So there's two ways to go about this that I'm just going to show you on the next slides because I don't need to type them in here. One is going to be, we could write a for loop that goes through every position in the list one at a time. And at that position, I'm going to select an individual student, which I will put in a variable named Stu. And then I want to know, is Stu's ID the ID I'm looking for? So I'm calling the getID method. And if so, I want to return Stu's name by calling the getName method. The directions do say here that if we don't find the student we're looking for, we should return null, because you can't return -1. That's not a string. So that's why I have the phrase return null here at the end. Now, we actually don't care about positions in this problem, so this is a good problem to use the for each loop for. We could say for every student, which I'm calling Stu, in the array list students, if stu.getID, so I'm asking the student for their ID, if it's the ID, I return Stu's name. And if I don't find it, I return null. All right, so that pretty much finishes up our discussion of linear search. So the next thing we're going to look at is this other type of search called binary search. And the idea is that if we know that our data is in order sorted from smallest to biggest, then we can divide our problem up into smaller segments that are easier to solve. So I'm going to open up this binary search widget to show you the idea. So I'm looking for the value 1328, and what I'm going to do is I'm just going to start in the middle, between 0 and 51, halfway is about 15. And I see the number 1194. Now that's too small. I need to find the value 1328. So I know everything to the left of me is smaller than me, so it's smaller than 1328, so I don't even need to look at them. So what do I do now? Well, now I'm going to look at all the values to the right of 1194. So that means I want to look between position 16 and position 31. I want to find the middle there, so what I'm going to do is add these. 16 plus 31 is 47, and 47 divided by 2 is about 23. I'm going to look there, and now I'm at 1446. That's too big, so that means all these numbers to the right are larger than 1328, and I don't need to consider them anymore. So now my search range is between 16 and 22. If I do the same technique as before, I add up 16 and 22, which is 38, divided by 2 is 19, and I check there. And we see that I have the value 1277, which is too small. So now I'm down between 20 and 22. Well, let me search at 21. Oh, still too big. And now I have only one more spot to check, and I found it. So it took me exactly 5 checks to find what I'm looking for. And for comparison, if we looked at linear search, this would have taken 21 checks to find it. With binary search, this new technique, it's only going to take 5. So what we're going to look at is how this strategy works, look at the code just a little bit, and talk about why it's so much better than linear search. Okay, so for this, I'm going to need to annotate a little bit. And let me find my color options here. Oh. All right, so the idea is that we're going to establish first these positions. So these are all the spots in our array. Notice the values are in increasing order from smallest to biggest. And what we're going to do is say that this is the low and this is the high to begin with. So our low is at position 0, our high is at position 8. The middle is just the average of the low and the high, so we add them up and divide by 2, which is at 4. And at position 4, we see there's the value 7. So here's where the interesting things start happening. So we know that we're looking for the target value 21. And we see a number that is too low. So that means all these numbers here we can automatically rule out by just checking the middle value. So what happens now? Well, we want to exclude all these values, and because our value here was too low, we're going to move our low position to be 1 to the right of the mid. So we're going to change our low to be 1 bigger than the mid, so that our low position is now at 5, and our high position is at 8 still. So this is now our new search range, and we're going to figure out the middle again. So 0, oh, I'm sorry, not 0. Our low was 5. So 5 plus 8 divided by 2. So that's 13 divided by 2, which is 6. And that's where our new mid's going to be. So we see there that there's a 12, and unfortunately for us, 12 is too low again. So we're going to be able to knock out these two numbers. They are too low. And once again, our low is going to become the mid plus 1. So now our low is going to be here at 7, 1 more than the mid. High stays put, and then if we average those two to find the next mid, 7 plus 8 divided by 2 is 15 divided by 2, which is 7. And look, at position 7 we have the number 21, and so we found it, and we are successful. So let's look at another example of doing binary search. So I'm going to clear these drawings and go to the next page. So this time we're going to look for the target value of 3. So the start is exactly the same. We're going to go through and think about all these positions. They go 0, 1, 2, 3, 4, 5, 6, 7, 8. Our low is going to start at 0, and our high is 8. And the middle is just their average. So 0 plus 8 divided by 2 is 4. Okay, so this time when we look at position 4, we see 7 and 7. That happens to be too big because we're looking for 3. So that means all the values to the right are bad. And what's going to happen here is, because our 7 was too high, we're going to change the high to be 1 to the left of the mid, and we'll say that high becomes the mid minus 1. So in this case, high is now, low stays at 0, but high is changed to 3. Now we're going to find the new mid position by adding up our low and high. 0 plus 3 divided by 2 is 1. And look there, and we're going to see that we have the number -2, which is too low. So these two numbers are out, and we're going to change our low. Let's grab a new color here. Our low is now going to be 1 to the right of the mid. So our low became the mid plus 1 because we found a number that was too low. So our low is 2, our high stays at 3. So we run this again. Sorry, that's not lined up very well. We're going to do 2 plus 3 divided by 2. That's 5 divided by 2, which is 2. So our mid is right here. And we look at there, and uh-oh, we are too low again. All right, so we're too low, and that means we don't need to check this value anymore. And the mid will become, the low will become the mid plus 1 again, because we were too low. And so our low is going to become 3. We're going to be, I should change one color one more time. Let's see, blue. So our low is going to be right here. Our high didn't change, and if you do 3 plus 3 divided by 2, well, that's just 3, right? 6 divided by 2 is 3. So our mid's right here as well. And we look there, and we found it. So I know that they got a little bit messy in here, but when we look at the code, it's really going to make this process pretty straightforward, I think, in terms of how we're changing the low and the high. All right, so what we've looked at so far is what happens if we find it. The one more thing we need to look at is what if we don't find it. So let's say we're looking for the value 16. So once again, we start with our positions. 6, 7, 8. Our low starts at 0, our high starts at 8. So here's low, here's high, and our mid is the average of them, so 4. And we see the value 7, which is too low, so that means that all of these numbers are bad, and our low is going to become the mid plus 1. So that means our low is now at 5, our high stays the same, and then we average those two to get the new mid. 13 divided by 2 is 6. And we look there and we see now we are still too low. So those two numbers are going to be out. So let me scribble them out. And our low is going to have to be 1 bigger than the mid. So our low is now 7, and our high is 8. And our mid is going to be 7 plus 8 over 2. So that turns out to be 7. So here's where something really interesting happens. We are too high now. So because we're too high, what happens is the high, oh, and I should write mid here. This is mid. So we're at a middle position 7, and there's the value 21. We are too high. We're bigger than 16. So that means we need to change the high to be 1 less than the mid. So that means the high would actually become 6, with the low staying 7. And if you notice, the high has become less than the low, and that's bad. So if we ever get that the high is less than the low, that means that we won't be able to find it. So let's look at what this means in terms of code. Now this is not stuff you would have to write on the AP test or that I would ask you on a quiz, but it's some code that you need to read, and I think it's good to understand the logic behind binary search. So the idea is that we have an array of values and something to look for. We start our low at 0 and our high at the end of the array, the length minus 1. And as long as our low is less than or equal to high, we keep generating the middle value, if the middle position, I should say, and the value at the middle position, if that's the target, then we found it, so we return that middle position. Well, what if we are too low? What if values of mid is less than the target? Well, that means the low should become the mid plus 1. So we're making the low go to a larger spot in the array to eliminate the values on the left. So this says if we are too low, change the low. And the else says, well, what if we're too high? What if values of mid is bigger than the target? Then we're going to need to change the high, like we were doing in the examples. And this loop keeps running over and over again until either we find it or the high gets less than the low. And if the high gets less than the low, then we're going to return -1. So don't worry too much about memorizing this. Like professional programmers don't usually have to re-implement the binary search algorithm. They just use a library that has this search strategy inside of it. So just know the strategy, like the basics of it and sort of the idea, but don't worry so much about reproducing this code. So this slide, just briefly, I wanted to mention that if you wanted to do binary search with strings, you're going to have to use a function called compare_to because you can't use the less than operator with strings. So this is just an example of it. Don't think it's going to be an issue on the AP test, but know that compare_to would allow you to say if one string becomes before another one in the dictionary. All right, so let's compare the kind of speed of these different algorithms. So let's say we're doing sequential or linear search on an array. On average, we expect the answer to end up to be in the middle. So that means we expect to check, oops, I didn't mean to click that, go back. We expect to check about half the values, so n over 2. So if we have an array of length 4, we expect to check about 2 values. We check 16 for 32, 512 for 1,024, and for a million items, 1,048,576, it would be 500,000. Wait, hold on. Let me erase that. I was about to say it right, but then I wrote an extra 0 there for no apparent reason. So it's going to be 500,024 and 288. And you don't have to know that number exactly, but that's what it works out to be. Okay, now let's talk about binary search. So the idea for binary search is it's how many times do you have to divide by 2 till you get down to one item. That's what happens usually with binary search. So if we start with 4, and we divide by 2, we get down to 2 things. And then if we're down to 2 things and we divide that in half, we get down to 1 thing. So it took us 2 divisions to get down to 1 thing. So binary search should take about 2 iterations on average to find what we're looking for. Now what about for 32? Well, we divide by 2 once, so we're at 16. We divide by 2 again, we're at 8. We divide by 2 again, and we get 4. 4 divided by 2 is 2, and then 2 divided by 2 is 1. So we had to divide by 2 5 times to get down to one number. So you can see that that's significantly faster, right? Instead of 16 for sequential, it only took 5 for binary. So you could go through this process of figuring out how many times you have to divide by 2. One thing that will help sort of think through these values I'm giving you here is this is 2 squared. 32 is 2 to the 5th. 1024 is 2 to the 10th. So that means we'd have to divide by 2 10 times to get down from 1,024 to 1. And 1,048,576 is 2 to the 20th. So it would only take 20 divisions by 2. And for those of you who know a little bit more advanced math, if you do log base 2 of your number of items, that's roughly going to be, on average, how many iterations the binary search algorithm will take to find the item you're looking for. So you can see that the speed is just totally different. Like binary search, very fast. Linear search takes a very, very long time. And this scales really well. If we went up to about 1 billion, see if I can write out 1 billion here. Okay, that's roughly 2 to the 30th. So that means it would take about 30 checks to find what you're looking for. Whereas for sequential search, I don't really want to write up this number, but it's about 500 million different spots in the array that you're going to have to check on average to find what you're looking for. So if your data is in order, binary search is definitely the winner. Assuming your data is sorted, definitely use this one. All right, so that's essentially what the next slide has. I think it's just a summary of that. And so which sort should you use if your data is not sorted? So the answer is you should use linear search, although you could try to do binary search, and if you're really lucky, sometimes it'll work out. I won't go through it on this slide here. Oh, heck, if you want to see it. I'm going to do the binary search algorithm just to show you what would happen. So we're looking for the value 4. Here are our positions. And that's a terrible 6. Oh my gosh, I made that even worse. Go away. Okay, so if we're going to look for the value 4, that means our low is going to start at 0, our high is going to start at position 8, and our mid is going to be at position 4. That's halfway between 0 and 8. We see the value 1 and we're too low, so that means all of these go away. And now our low is going to be at position 5, one more than the mid. And then what's halfway between 5 and 8? 5 plus 8 divided by 2 is 6. So here's our mid. Oh, look, we found it. Yay! So maybe binary search does work if it's unsorted. Let's do one more example just to see if that's really, really true. So let's say instead of looking for 4, we looked for 6. Same as setup. So we got 0, 1, 2, 3, 4, 5, 6, 7, 8. Our low starts at position 0. High starts at position 8. We're looking for 6, and our mid is at position 4. So we see a number 1 there, and that's too small. So we're going to cross out all these numbers. Uh-oh, we just crossed out the 6, and our low would go here. So the algorithm's not going to work in this case. So no, do not do binary search on unsorted data. You can try it, and you might get lucky, but don't count on it. All right, that's a real fast run through of how linear search and binary search work.